Hello, my name is Roy Rosenberger. I've come today to speak to you about image analysis as it is used in the recycle of fibers for the paper industry. We have developed many ways of analyzing the process and the dirt that we're trying to remove from the process. Commonly, it's residual ink. Why use a dirt counter or an image analysis system at all? Well, it's primarily to get consistent quality reports, measurements through the whole process. There are two ways of measuring, or two reports that we can get. One of them is designed for process control. It is not as sophisticated as the TAPPI requirements for TAPPI 563 or 213 or 437, which we will discuss. These are used for analyzing the final product as it comes out the back door of a mill that is shipping pulp to another mill. The transition is quantified using the TAPPI measurement standards. The other method is one that is used to control the process itself. Not quite as sophisticated, but is more revealing and indicative of what is necessary for the process. What we're going to be doing is covering the equipment, the theory, and how to set thresholds and various elements like this, the calibration of the units using the traditional method or the process control method, and TAPPI 563, and the measurements, the dirt count, ppm reports, and so forth. And then we'll talk a little bit about stickies and how you can quantify the measurement of stickies. The measurements, we're going to use primarily white stock, but we can also use OCC that is used in the production of linerboard. And last, we will spend some time talking about stickies and TAPPI 563. The system is composed of several elements: an image analysis system, a scanner, or it can be a camera, and of course all the necessary accoutrements that go with a computer-based system. The computer can be an ordinary computer, but the scanner is a little bit special. The scanner should be a graphic arts quality scanner. The one that's shown here in the photograph is distinctly different than the one that is used in the laboratory of a recycle mill. This is an HP 8200 scanner. You'll notice that it is fitted with a block used to hold down the specimen. The specimen, as you can see here, is quite wrinkled. This scanner is different than most scanners. There are a few of them out in the market that have on them two bulbs. Inside the scanner, this scanner, it has two bulbs, and I'll explain this a bit on the slide. What you see here are the types of hand sheets that can be analyzed. They can be dark, light, anything really from the process. There are two types of imaging devices, the scanner and the camera. The most important aspect of the measurement system is resolution. We will acquire a digitized image, and most of our measurements are going to be in the gray scale because really residual ink is black and we don't need to go to color. But on occasion, we will go to color for measuring things like OCC and linerboard. The camera. This is what differs in the technology of the scanners and the cameras. The camera moves and across the image, acquiring one frame at a time. It's typically used in TAPPI 563. Whereas the scanner, the specimen does not move. and the line scan camera moves along and acquires the image. You'll notice that there are two bulbs. Two bulbs on the scanner. This gives you actually symmetric illumination. As I showed you earlier on the unit that is used in the demonstration, the HP 8200 has two bulbs giving even illumination and eliminating shadows in the image. The heavy block helps to overcome any cockle that is in the specimen. As you can see here, the block is very special. It has a white face. It weighs about 2 kilograms, and it holds the specimen flat to eliminate any or minimize any cockle. The two bulb illumination is very important, and it does minimize the effects of cockle and any fiber shadows. This way we can find the dirt through the whole hand sheet. Resolution is very important. Most of our specs are very small. We're looking at specs of 0.01 square millimeters. To acquire the image of such a small speck, you require a resolution of at least 600 ppi. Moving to higher resolution of 1200 and 2400 ppi, we increase our ability and our accuracy of the measurement considerably. In production, though, we found that 600 ppi is adequate. For measuring with TAPPI 563, a minimum of 1200 ppi is required. It really works much better at 2400 ppi. But remember, when you go up in resolution, the image increases in size dramatically. A digitized image of dirt, for instance, here you see an idealized image of dirt. It's a black oval. Each one of the squares represents a sensor inside the camera of the scanner or the camera-based system. The sensor picks up the light signal, and it will scale the light signal from 0 to 255 in strength. And thus we can see the background is white and typically is 235 gray values out of a scale of 0 to 255. In the black area, typically it would be 55. This will vary, of course, with the intensity of either the background or the speck itself. But you notice one peculiar thing about this. The image is not completely covered, or the sensor does not completely resolve or obtain an image of the edge of the dot. This edge effect ends up in the image as a gray value that is not really representative of the speck itself. You'll notice the gray pixels around the digitized image. We're familiar with this pixelization from the TV. They use this to blank out faces of criminals on the show or areas that they don't want to show. But this edge effect is very important. As you go up in resolution, the edge effect becomes less and less of a factor in the image and improves the accuracy greatly, primarily because there are more subtended pixels than there are on the edge. So the weighting factor is very important, and it really is the resolution. How do we acquire the image? We must separate the speck that we're looking for from the background. Now here you see that same speck on a scale from 0 to 255. In the computer program, we can set a threshold below which all of the pixels that have an intensity below the threshold will be considered as a part of a speck. Above that, it's considered to be the background. This threshold is flexible and can be moved in the software up and down. What we find, though, in practice is that the threshold, once set, does not follow with the background as the human eye does. We can compensate for this in practice by using an offset. We can first set the threshold and back calculate from the background an offset number. It's generally in the order of 15%, somewhere around 33 or to 40. It's 15% of the background is normally what we use as an offset. So that when we go into automation, we measure first the background. We recover the offset from memory, and from that we calculate the position of the threshold. And each object is then based upon the pixels that are discovered below the threshold. And this gives us an automatic way of compensating for handsheets of varying colors, varying backgrounds. As I said, the pixel count below the threshold becomes a consideration in determining the value or the size of the speck of interest. The software will go through the entire image, determining which pixels qualify as part of a speck, and it will then determine which one of those pixels is touching another and begins to form an object. The object is held in memory, and all the pixels are then counted, and a size determination for the size of the pixel is multiplied by the number of pixels in the speck. Very simple, very easily done, or very elegantly done in the software, and very rapidly. A typical setup display looks like this. As I said, the first thing that happens is the histogram of the entire image is extracted from the image that has been scanned in to the computer. This histogram is displayed, and in the setup mode, one can set the threshold and back calculate the threshold. You can see here the threshold is back calculated to be minus 40 at a threshold of 91, which is set on the histogram. This can be moved back up and down in the software quite easily, and the calculation is automatically made. This means now that any speck or any pixel falling below 191 will be extracted and considered as a part of an object. This is typically done on all all images that are brought into the system. Now, the measurement is an estimate. The estimate improves in accuracy as the resolution is increased. This is typically what happens at 600 ppi. You see on the left a speck. The speck is idealized, and then it is formed. You see the perimeter of each of the specks is computed, as well as the size by counting the number of pixels that have been thresholded, and the polygon in this particular image describes the perimeter. This calculation of the perimeter is used to define the shape in the software. Now, the area, as I mentioned before, is computed from the calculation of the size of the pixel multiplied by the number of pixels in the speck. In this case, is at a 0.042 square millimeter speck in the idealized example. Well, how do we calibrate a system? One of the mechanisms we can use is the dirt estimation chart, which you see here that we can obtain from TAPPI. This card is readily available. It costs $60 from the TAPPI library and can be obtained to have typical sizes on the dot or on the card. These cards have been used for manual inspection for the last 69 years, since 1936. And the dots that are shown on them are fairly accurate. You will see later as we go through that there are variations within the dots. They're not perfectly done, but they're adequate for the job at hand to calibrate the system and to emulate human inspection. At 600 ppi, we place this card on the scanner and very simply make a scan. You see here, to acquire the dot accurately, to emulate what is on the card, we can set the threshold at -105. I will point this at 105 and a threshold of about 138. This gives us a reading of 0.022 square millimeters. But remember, the card is idealized. It's perfectly white, and the speck is standing right out on the surface. If we do this, we can get a very good measurement of the dot. This means that the scanner is working well. Everything is tuned up very nicely. At 1200 ppi, you see that we get a much finer resolution of the 0.02 dot, and its actual measurement is 0.02. Whereas in the previous example at 600 ppi, it was 0.022. So this shows the effect of calibration. Remember, the spec is still an estimate of the size in any system that has a resolution of 600 ppi. It is fairly accurate enough for what we're going to do in process control. A moment on shape. Shape is the same as circularity. Circularity is a concept that was originated by Archimedes in about 200 BC on the island of Sicily, which was then called Syracuse. He defined the relationship of the perimeter to the subtended area by squaring the perimeter and dividing by the area. This was, he determined, at the, for a perfect circle is always 4 pi. It can never be less than 4 pi. It's always 12.57 for a perfect circle. Fortunately for us in the paper industry, residual ink and dirt is mostly roundish. It is very close to a circle in most cases. It is roundish. You can see that there is one speck that has been calculated at a circularity of 28. This is typical. Roundness, in my judgment, goes from 12.57 up to about 40. And then beyond that, the objects become clumps and fibers, and the number keeps on rising. It is asymptotic to infinity. Shape is the same as circularity, and as I mentioned, it has a minimum of 12.566, and you can, on some of the image analysis systems, measure up to 5 different kinds of objects with varying shapes. A bit on luminance. Every speck is different in its luminance. There is a gradient across the spec. Inside the perimeter, we can measure all of the spec luminance values. Just what is its reflectivity, and we can get the average. Now, TAPPI 563 stresses this in computing the equivalent black area of the speck. In other words, if you have gray specks, they are different from black specks. And it is important to know which you have and how many of each and so forth for TAPPI 563. For process control, it is irrelevant. You have a spec or you don't have a spec, because the equipment that is used for the refining process or the cleaning process doesn't care what color the spec is. But 563, we are concerned about it. It is a useful tool for separating gray specks from black specks, but there are other variables involved which we'll discuss in a moment. In a typical image analysis system, every spec is classified by size. And as you see here, by clicking on the image, you can get the values for every spec. Here you have the solid area and the holy area. What's the difference? The holy area, if the spec has a hole in it, the area is different than the area subtended by the perimeter. So the subtended area is a solid area, and the holy area is the area with the holes in it. So we report both of them. Sometimes it is important in the process control depending upon what stock you are measuring. The perimeter is measured for every spec, and you can filter out things that you don't want in the image. When you scan in an image of recycled stock, you may have present shivs along with the dirt, and you may want to filter them out and have only the dirt reported. Or just the opposite, you may filter out the image of the dirt and have only the fibers reported. At the bottom of the setup screen that you see here, on the left-hand side, you can set the smallest and the largest spec that you are looking for. In this particular case, we have set the minimum spec size to be 0.02. But you can also set the shape. If we only wanted to measure in this image of the handsheet the dirt, we would set the range to be perhaps between 12.566, which is a perfect circle, and somewhere around 50 to exclude any fibrous materials from the measurement. The same thing can be done with the luminance. If it were relevant, you could screen out all the black things and keep only the light gray, whatever. It's very seldom that you use the luminance, but there are occasions which we will cover when we get to the POMAC analysis of the black filters and TAPPI 277. To measure. Very simple. I'm going to show on the scanner exactly what is done. This is a typical scanner and the block, and here you see a sheet that was prepared for laboratory testing. It's very busy. It's got a lot of dirt on it. It was artificially doped, but is a good example. It is all wrinkled up. You can see just how wrinkled it is. And there's a lot of dirt on it. We put it on the scanner and position it the same way each time. This makes it easy. And we put the block on and very simply place it. That is all that is involved with the measurement. We can then cause the scanner to measure or to take an image of it, and away we go. We calibrate. We can see that the scanner is working all right by using the dirt estimation chart, but we'll show you in a minute that the estimation chart is really used only as a reference for the measurement. The chart is available, as I said, from TAPPI. We'll scan it in at 600 ppi, we'll measure it, and we'll adjust the threshold repeatedly until the sizes agree. If we don't get a calibration, we have a problem with the scanner. But we will not use the threshold setting that gives us the optimal measurement for the dirt estimation. Why not? Because that is a perfect card against outstanding black dots against a perfect white background. In process control, we don't encounter that. We very seldom have a perfect white background, and we're trying to find dots that may be covered with fiber in the hand sheet. And so the calibration or the sensitivity using the calibration card will give us erroneous results, or won't give us the results we're looking for. But we can use it to see if everything is working properly. What you saw coming up just now on the screen is a typical report. We'll show you the dirt count, how many specks were counted, the ppm, which in this case is enormous, and we'll give you, we'll go back again, we'll give you the specifications by all the specs in classes of size, counts, the area, the ppm, and the luminance in each of the size classifications. This is good for process control because you can then narrow down which piece of equipment may be giving you problems and analyze the results. Everything is dumped into Excel spreadsheet, which comes in the software package. So you have the controls for actually process reports. Calibration. In 563, you use a calibration plate and you input factors that are provided with the plates. The plates come from TAPPI, calibrated by Papercan in Canada. And as you see, there are correction factors given in the letter that comes with the plates. We will use primarily the dark dots. These dark dots are the primary calibration for TAPPI 563. TAPPI 563 mandates that you set the threshold at 15% of the background, and we do that automatically in the software. We set the scanner for 1200 ppi minimum. 2400 is much better, and the results should be 5%, plus or minus 5% of the reported measurement or the reported size. Now here you see the calibration factors that came in the letter, put into the software in the calibration mode. The background of the chart is also input so that you know what it is. And then here are the actual calculations that were made of the chart. This is a typical analysis of the chart. You'll recognize the thresholding colors that have been placed on the dots. Each one of the colors is representing a different size dot that has been measured. The chart originally is gray, and I will show you that during the lab phase of the series. The chart is scanned in initially during the calibration phase, and down below is the K factor called out in the specification that is calculated from the chart. What is typical of the measurement system in general? we're calculating every time we make an image of the hand sheet or the tear sheet from the process, of the area, the shape or the circularity, and the luminance or the reflectivity of every speck. All three characteristics are used in the separation of stickies, dirt, fiber, and hairy stickies. You can classify by any process problem. There are various ways of separating stickies. Stickies are really a problem to analyze. To get them, you must separate them from the process, and there are various devices available to do this. The POMAC is the easiest and probably one of the better ones to be using. It is automatic, and you get consistent results from them because the human factor is minimized. We can analyze the filters that come from the POMAC quite easily using various techniques. This device is different than measuring dirt, obviously. It is an automatic device. Having several elements, but the output is a filter paper that is nominally 8 inches in diameter, collecting all of the specks or trash that accumulate from a screen that is a 100 micron screen. These can be processed using several methods, or a couple of methods. One of them is a laminator technique, in which the filter paper is processed through an ordinary office laminator with mylar films, and the stickies will stick to the film preferentially, and the rest of the material is separated. In the image analysis system, we simply count the stickies that stuck to the film. The second method is TAPPI 277, where the white paper that was developed by Voith and is available from them, containing an aluminum oxide coating, or maybe a calcium carbonate, lightly adhered to the paper, that comes off when a carver press is closed at a known pressure and temperature. It will then transfer the white powder coating to the stickies preferentially. When separated or taken out of the press, the paper is removed and the excess white powder is brushed off and any other loose materials, leaving only the stickies and whatever material is left behind. The white aluminum powder and a press is the same as 277, but there's a powder that can be used instead. But the idea is to separate the stickies by some means. All these techniques, the image analysis, can be used. And here you see an office laminator, and the laminate is attached to, or the filter paper is attached to it and separated, or all the dirt is measured, and then you separate the film and you make a second scan and measure the stickies. Now, what you see here is the Domtar laminator method on the right and the TAPPI 277 on the left. The 277 is a black filter paper, and in this case we want to analyze all of the materials that the POMAC has separated from the process. And the aluminum powder, or the Voith paper, has been placed over the top of the filter paper, put through the carver press, and all of the residuals remain, and we can separate them in the image analysis system by their type. The fibers are separated from the stickies and reported separately, and the hairy stickies, those that are attached to fibers, are also analyzed as a separate item. The image analysis system in one scan can separate all three. The color extraction. This is really Image Analysis 102. It's especially good with linerboard and OCC. And as I mentioned, the TAPPI 277 does a bit of this also. It can extract white objects, black objects, long objects, using the ASL, the area, the shape, and the luminance characteristics. And basically, the camera is a color camera that acquires an RGB image, a red, green, and blue image, which then can be recombined to extract the cyan, magenta, and yellow images by recombining the RGB in different ways. This can all be done inside the computer to do the separation, which we do automatically in the Verity IA system. In this case, we use a dual thresholding technique, which is a bit more computationally intensive than in the ordinary dirt counting environment. With that, we have concluded the presentation. I will now show you in the laboratory how we can do these various measurements. We're going to pick up right away with a little show and tell on the TAPPI 563 method. TAPPI 563 evolved from the T213 and TAPPI 437, which were manual techniques, very subjective ways of measuring equivalent black area. In the early days of the industry, they wanted to tell everyone just how black the dirt was that was coming out of the process. Light gray things were acceptable and dark ones were not. And so they had a subjective way of measuring or reporting what was equivalent black area. TAPPI has issued with a new standard, the 563, which is an automated way of using image analysis to do the same thing that for 60 some odd years was reported subjectively, a highly variable measurement which very few people had confidence in, but was used and the numbers were reported. In any case, we've automated it and made it more objective measurement. With this measurement, or with this new methodology that was recorded in TAPPI 563, there came these cards. Now on the scanner base, you see the white standard. The white standard was necessary for the camera-based systems. The scanner, we have no control over the whiteness or the brightness of the bulb. That is automatically done in the scanner. But we use the card to warm up the scanner, and that is in the regular procedure for the calibration, and you will be prompted by the software to load the white card in and then the black card. And the black card, you see here, is not very good on the reflectance with the light, but this is black. And then you are also provided with light gray dots, which you can hardly see in this image. And the fact is that we don't use this card in the calibration of the device, but in the original standard it was specified and issued but is not used. The dark dots that you see here are used. And the procedure I showed you during the lecture portion, these dark dots are used to calibrate the scanner and the software. There are 16 dots here, of which you can only see about 4 on the image. And they are arranged inside of a square that is 30 millimeters by 30 millimeters. This is intentionally done so that the cameras can acquire the image. Basically, 563, when it was originated, was designed for the cameras that were the only devices that had high enough resolution that were commercially available to acquire a high-resolution image, but unfortunately are limited, and still are, to an area about 30 millimeters by 30 millimeters. This means that when they scan or try to quantify, they are only measuring in this very small area. Here you see typical hand sheets. This is not a typical hand sheet. This is one that was doped up here in the laboratory at North Carolina University for the students to examine. But it is kind of typical. It is in a hand sheet dryer, it will be wrinkled like this and full of shadows, if you will. You can see the shadows here. And these, if you do not use a two-bulb scanner, will interfere with a measurement in a dry form. But we will show you a wet technique that will be used or should be used in process control, which brings me back again to the subject that the TAPPI 563 is a way of quantifying the amount of dirt that is in the stock or in the bell that is shipped to a mill that is not integrated and is interested in quantifying the quality of the stock that they are buying. So when you ship, or when the mill producing the recycled fiber that has been cleaned will test to 563 or some other method of quantifying the amount of dirt that is present and certified to the buyer that in fact the stock is to the standard. This hand sheet that you see here is used in process control. Process control is distinctly different than when you're shipping a product. In process control, you are interested primarily in how well the stock cleaning equipment is functioning. Are the various filtering, cleaning, screening devices working properly? Is the stock as received to the quality that you have purchased? So you're not interested in quantifying the light gray things. You want to know how much dirt is there. How much do you have to remove and how much remains? It is a totally different environment than when you ship the stock to a buyer. The test is a bit more comprehensive and simpler in the methodology. We'll take this same hand sheet that is wrinkled, and I want to show you how we would do it in a process operation. Now here in the studio we are limited. This hand sheet has been dried and we've handled it many times, and you can see, perhaps I should go over here again to the table, and you can see here there is writing on the back of the hand sheet. That is significant. I want to show you what that does in the process. But the student has quantified on the back of the hand sheet by putting on ballpoint pen the measurement or some notes for his own reference. Normally, this hand sheet is produced in a hand sheet mold. The mold, you put a blotter paper over the top of it and you couch with a heavy roller. By squeezing the excess water out, the hand sheet will adhere to the blotter. When you take it off the hand sheet mold, the blotter paper is on the top, and what we're suggesting is that you simply bring the blotter paper with the hand sheet wet over to the scanner, position it on the scanner, put the block on the top of the blotter paper and the hand sheet, and then do the scan. Very simple, very quick. And you can measure then all of the dirt in the handsheet. In this particular case, we'll illustrate just what you can do with such a system. The writing is on the back of the handsheet, and we'll dip it in the water, simulating the creation of the wet handsheet in the handsheet mold. And we'll put it on a white background, simulating the blotter paper, and we'll roll off the excess water, and we will very simply blot off the excess water, again making it relatively dry, so we don't want to screw up the expensive 8200 scanner. And I will show you this over here on the table. I don't know whether we can focus this or not, Bill. Is that in focus? Yes, you can see that the writing shows right through the wet handsheet. This means that we can, in fact, measure all of the dirt at one time. We'll put the blotter and the handsheet right on the scanner. Now, the scanner system has been loaded, and we will set up the test. Very simply, go to Set Up Test, and we will select the scanner. And with the scanner, we will make a preview scan to find out where this image is located on the scanner bed. Now, the scanner always makes a rectangular image. It will transport the image directly into the software so that we can then measure it. But the scanner is designed to just make a rectangular image. Now, that's what you saw. And we have the ability to adjust the scan area using various controls on in the software. Looks like we go all the way to the edge, and actually the measurement is just about right. But you can see how we can adjust the scan area. So we'll do a normal scan. Now, every step that we take in this process is recorded, so that when we later push the Run Automatic Test button, you can, in fact, it will go through each step that we did manually. It will do it automatically, so that we don't have to do this but one time on the setup, and we can make repetitive scans. Now we have the scan into the software, and you can see that in fact what did I do? I turned off the entire program. I will load it again. There we go. By mistake. What we can do, you can see the writing is showing through, meaning that we have an image of all of the dirt through the entire handsheet. So we don't have to flip it over, we don't have to dry it, we can see all the dirt at one time. And we can position the area of interest in this handsheet. So we don't want to measure the handwriting, so we'll set up an area of interest that does not include the handwriting, and we'll finally adjust this. We'll get it below the handwriting. So we have adjusted an area that will be an example, but you can see that we can adjust the area that we will measure in. So any writing on the hand sheet will be eliminated, and we will not include it in the measurement area. And we will then set up the test further by designing the actual threshold. So you can see here that we have a threshold set of -35, about 15% of the background as suggested by TAPPI, and that is a threshold of 204. And we measured the background. We got the statistical mode, the mean, and the median. Now, what is the mode? Many people do not understand this. Statistically, this is the most populous pixel color. It is the one that is most prevalent in the hand sheet. The mean, of course, is the average pixel intensity, but the mean includes also the dirt, the very thing that you're trying to measure. The mode is more typical of the background because it's the most frequently occurring intensity. The mean in this software is calculated by double calculating the mean. The first calculation of the mean is for the overall intensity within the image or the analysis area, the area of interest, and the standard deviation is also calculated. The mean is then recalculated within the standard deviation so that we're narrowing down and eliminating most of the dirt when we recalculate. So the mean may be more typical of the background than the mode in many cases, but we'll stick with the mode in this particular example. We have done all the settings. We're filtering out everything that is less than 0.02, but I can tell you that this hand sheet is very busy, and we'll make the calculation anyway. It's kind of typical of what may come out of the pulper, but you can see that we counted 1,486 dirt particles in that small area of the hand sheet. Very busy. The ppm is out of sight. It's 37,000 and some. Each one of the specs is classified into categories. We have 207 at 0.02 and above, even though we filtered out because we got rounding errors in there. Let me set that at 0.02 and we'll do it again. Yeah, now we don't have the rounding errors. You can see the this is 0.01, 0.02 to 0.03, and so on down the line. All of these specs in the image are color-coded according to the classification. At the bottom, you see that we have reclassified, and we have all the roundish specs, there are 1,300, and we have some long, oblong shapes at 27 and one of them. Down below, we have the statistics, and we can, in fact, find the smallest object by clicking on it, and it found it up there. I will magnify the image now just to show you what is going on. And here you see a magnified image. And we'll go further. You can see them all, and this will be very handy for you. I'll click off the zoom, and each one of these, each one of the specs, we can get the size of them and the luminance value, the perimeter, the circularity, and so forth. You can see that the small dirt here is circular. That's 12.57. So you've got a lot of data here that allow you to tune up the system and diagnose problems in the process. Very quickly, a review. This is, imagine this is a blotter paper, and this is the wet hand sheet right off of the couch roll from the hand sheet mold. And we scanned it in, and we can very quickly diagnose the system. Now, as I mentioned, we're recording all of the steps in the process. And as a result, when we go back and push the run automatic test, it will go through and make the test automatically. Just clicking, it goes and does everything on its own. It reproduces exactly every step along the way, including the threshold and the offset calculation and the scan. You can see perhaps the scanner head moving down. And maybe, I don't know whether you can't see the two bulbs, but I can see the two bulbs in the scanner head. The scan is complete. It should be loading in. And what is going on here? Ah, here it goes. And you see the computation proceeding. It's counting away, and here we go. We have 1,415 specs. And the test is now complete. It is that simple. Things that you should know: you can export the settings. What you see here is the round handsheet. All of the settings can be exported anytime you wish by just going to Functions, and you can export it, and you can email it to another user who has the same system, and they can very simply load it into their system by using the import controls. I exported it, and now I can import it. That is basically the system at work. There is nothing else to tell you about it. It runs very quickly and very easily. Just run from the wet handsheet for process control. Bill, I think we're finished from the Stickies measurement. Stickies is a different problem altogether. As I mentioned to you during the lecture portion, we can use a POMAC device for separating the Stickies from the process. This is an automatic machine. It works quite simply. It is a little bit pricey, but the results are consistent, and they are used in the process readily. We get from the POMAC, ooh, a lot of gloss on there. There we go. This is a typical handsheet that was produced on the POMAC. This can be used, as we showed you before, in the image analysis to count all of the Stickies. The laminator is used to heat the Stickies and produce another sheet that is from the process. This contains only those materials that stuck to the laminator. You can place this directly on the scanner and measure it just like we did the wet hand sheet. The process, as I mentioned during the lecture series, also produces a black hand sheet, which you see here. Against a black background, that's not too clear. I'll move it over against the white, but you can see now it is black and white. The white portion is the Stickies. You can perhaps see the brown, maybe not so good. I should put these on this on the scanner and show you there. But in any case, this has been processed through the Carver press and using the Voith paper to activate the stickies and identify the stickies as separate from the other tramp materials that came with the process. I will show you now another technique. This is a hand sheet of OCC. It looks brown, as it should. It's linerboard. It's old recovered cartons, old cartons. They come from grocery stores, from Best Buy, from the department stores. I think maybe even some of it is curbside. But in any case, the OCC contains stickies. The stickies that are most interesting to the industry, the linerboard industry, is the wax and the low melt point materials that come in the process and eventually end up affecting the printing and gluing characteristics of the linerboard. And this hand sheet came from Fox Valley Technical College, where we produced this hand sheet under controlled conditions. It is doped. We took recycled fiber and mixed it with virgin fiber so that we can control the amount of wax-containing cartons in proportion to virgin stock. This one has the stickies of most interesting to the linerboard embedded in it. And as you can see, it is perfectly normal. It is fairly uniform. But when we take this same hand sheet and we dip it in water, and roll it out,
you're using a black plate this time instead of white. Is there a reason?
yes, this is a black background, back plate, because in fact our stickies, the hand sheet, now, I don't know whether you can see that there. We'll put it on the stage again. You can see now that they're white specks, or light colored. What has happened is the wax has, in the process of making the hand sheet, drying it on a hand sheet dryer, the wax has now melted and come into the linerboard or into the OCC and made the fibers waterproof. With the water has turned all of the unaffected fiber dark, but it has remained lighter colored areas where the stickies are present. We'll put this on the scanner and we'll tune it up and show you that we can in fact quantify the count of stickies and the area occupied by the stickies using just the same software, but set up a little bit differently. We will, let's make a scan. We'll do a preview scan. There it is. For our real scan, we'll only scan in grayscale, and we'll move over the area to the left, and that's just about right. Okay, we'll make it a little wider. And we'll do a normal scan, 600 ppi. We'll just get a grayscale image and see how that works. This is a very simple test. It is not as involved as running on the POLMAC, and it gives some of the results that a POLMAC would yield. It is sensitive only to those low melt point waxes that will melt in the hand sheet dryer. We'll center the area of interest, eliminating any edge effects, although we do have a nice fat sticky at the top. Yeah, we can do this. And make it a little bigger. Okay, we're set. Now we'll get into the design to test and see that everything is set up properly. Yeah, okay, it's down to 16 and it looks like a lot of stuff. Now these stickies are generally very large. Small anomalies we're not interested in. If they're very small specks, and so we'll limit our investigation to objects that are greater than 2.25 square millimeters. Yeah, good. We'll do the measurement, we'll test it out. And it's all done. Now you see there the stickies, the quantified stickies. A very simple test. I will turn off the setup mode altogether. And as you can see, in the lineup of tests that are available, this is the round OCC stickies. This is the white one we ran previously. And we have selected the right one to run automatically. And we'll just click the button and away it goes. There we are. That's all there is to the stickies measurement. Very simple, very straightforward. I want to show you now the method for measuring the black hand sheet from the Polmac device. This hand sheet is a very busy hand sheet. A lot of things going on here. We have fibers present. We have the white stickies, and we have the hairy stickies. And for those who are unfamiliar with hairy stickies, they're the stickies that are stuck to fibers and sometimes cause problems in the process. I can see these hairy stickies, and I will show you an example of them. I will simulate the test. I have already acquired an image, and I will use it. This requires not using a dirt counter, but to use a more sophisticated program, paper and print quality, one that is able to acquire the image as the dirt counter did, exactly the same way. But in addition, it is able, in the analysis, to separate up to 5 different objects with different characteristics altogether. For instance, we have the fibers, and we have the hairy stickies, and we have the stickies. We have 3. It's able to do 5, but we're only interested in 3 in this particular case. Setting up the software, you see here, automatically, we have the same ability to have multiple tests configured in the system. You can select any one of them. And one little feature I didn't show you before, you can click off and protect the configuration. Watch what happens at the top of the screen. The setup capabilities disappear altogether. There's a much more secure way of doing the same thing, which I won't go into during this portion of the demonstration. But those who are interested can contact me afterwards. We selected the master screen, which is what the name of the POLMAC is, a POLMAC master screen, and the black image area. So we're done with that. This is the scanned image that was stored in memory, done previously. And you'll notice up here in the right-hand corner, we have 3 classifications. We're set up to use only the first 3, stickies, fibers, and hairy stickies. We'll go into the setup. Now, each one of these has its own AOI. I don't know whether you can see the screen flicker when the new AOI comes up, but each one of them has exactly the same AOI, or area of interest. But in the measurement, all 3 will be independent measurements. So we'll set up the first one, stickies. Here you see that we're measuring now light objects against a dark background. It's very simple to change back and forth between the 2. And you can go either way. This happens to be a black hand sheet. So the effects the threshold has to be above the mean instead of below the mean. Very easy. You can see the image is bimodal. There's an awful lot of things in this thing. This peak is probably the white stickies, and these are the hairy stickies down here. But we're setting up stickies in the first AOI. We'll set the minimum size to be 0.08 and above. The shape we're looking for is those that are round, between 12.57 and 45. The scroll bars control this very, very carefully and very easily. And the average luminance now, we want only the white materials. So we'll set the lowest area to be 130 to 255. And this will do the stickies. And as before, we'll do the measurement very quickly. And it will give us the same report that we had in dirt, a little bit more sophisticated because now we're reporting luminance also. But this is a big, busy image. It keeps a computer very busy, so it takes a while to calculate. And we can pull this report down, and you have the same detail that you had on the dirt counter, but we're going to be able to do 3 of them. So we'll take the next AOI, and that is the fiber. And we'll do the same thing. It is set up 0.08 again, but this time the shape is 45 to 10,000. So we want everything that is not round. And the luminance, though, we want only the darkest of these. So it goes from 0 to 109. This was set up previously, and we'll go ahead and make the measurement. That's a busy one. It takes a while because all those jagged shapes in there, doing that perimeter keeps the computer very busy. There are 752 of them. And as before, you can click on them and get the details about any particular one. Now we'll go ahead and do and you have the same reports as before. We'll go ahead and look at the hairy stickies. These, 0.08 is a minimum again. And we're looking at anything that is not round because these are the jagged fiber. But the luminance value is brighter than just the fiber by itself. So it's 110 to 255. We'll do the measurement again. So the filters now become all important on this particular measurement. It's not measuring. I didn't click it right. Here we go. Okay, now we got it started. And it will be busy for a while because there's a lot of hairy stickies in there too. Now, anytime you may not be interested in this level of sophistication, you can use the dirt counter just to count the white stickies and don't count anything else. But this one allows you to do, as I said, up to 5 different ones. We're only doing 3. But here you see the entire report. It's again protected. I'll run the test on this image, meaning that I can test the configuration that I have just made, and by testing it on the image that I have present at the time. Now it's going through all 3 tests automatically. And the results are dumped into an Excel spreadsheet on every test. In this particular case, when I'm measuring the image using the automatic controls, it will be transferred into Excel. And I think I can show you that. Yes, the stickies are reported, and it's busily calculating the fiber. And now it's going to do the hairy stickies. We've demonstrated everything in the laboratory of the typical recycle processing mill. We've showed you how to do the process calculations for the dirt content, watching it everywhere from the pulper on through to the finished product. You can monitor the amount and quality of the dirt, and then you can also measure TAPPI 563 if you're shipping or selling the product to another mill. And that pretty much concludes our laboratory. Thank you very much.